Hello, everyone, and welcome to this month's learning series as part of the Fault2SHA working group. I'm absolutely delighted today to welcome Francesco Vicini, one of the founding members of Fault2SHA, and he will be discussing statistics and probabilities in fault-based seismic hazard assessment. So the hope today is he's going to explain some of the background to the Fault2SHA outputs and working groups, calculations of hazard calculations, and also behind some of the tools that some of you actually may want to use when trying to do some fault-based hazard assessment yourselves. So some of this will be quite introductory, hopefully really bring together people from different disciplines to help you understand, and then some of it will move to more advanced topics as well. As always, the point of these learning series is to really help all of us working at looking to improve using faults in seismic hazard assessment, understand what's going on behind all the research. So it's an opportunity to learn and an opportunity to ask questions from those who really understand what they're talking about. And who better than Francesco Vicini to discuss this topic, as he has written many papers and produced fantastic code looking at creating these calculations. And I really value Francesco as a colleague and as an educator to me when he explains things. He's great at explaining them and understands them very well. No pressure to you, Francesco, in your talk now. So Francesco, as you're probably all aware, works for the INGV, the Istituto Nazionale di Geofisica e Vulcanologica in Italy. And so I hand over to you, Francesco. Again, thank you so much for presenting today, and we look forward to your talk.
Thank you, Joanna. Thank you for a beautiful presentation. Too much pressure for me now. Anyway, what's in this talk I will try to have is a very primer talk that I hope that could help you to understand some basic concept in PSHA, probabilistic seismic hazard analysis. So I hope that at the end of this of my talk you will move a step forward from a very too many dab to say, okay, I understand something and I can now really understand the PSHA purpose in a different way. So I will talk about very simple concept, and we will move through 5 sections, starting to defining what is event, probability, conditional probability. That's a very important aspect of our research, and we will move through to see some distribution, in particular Poisson distribution, and we will have a quick look to the Gutenberg-Richter, and then at the end I hope you have time to try to do a calculation of the hazard using a very simple model, but I hope you can really understand what we do with seismic hazard assessment. This is just a list of a very short list of the references that I used for producing this talk, but many other papers can be found in the reference of the more recent paper, and also, as Joanna said, in some of our works that I hope you will read in the next months. So I think we can start, and the first concept we have to introduce is what is an event, because event is as the basis of the PSHA. Events in probability is defined as a set of outcomes of a random experiment. For example, if we have a die, that is the first and most basic example we can do. If we have a die, we can say that we define the sample space, denoted as capital S, is the collection of all possible outcomes. And in this case, because it's a 6-face die, we say you have the sample space that is given by all the number from 1 to 6. So the outcomes in the event that the number is equal to 2 is given by E1, and is used there's a notation to indicate the outcomes in the event E1 is given by the number 2. The outcomes in the event that the number is greater, for example, is greater than 4, as the set A2, this one, so is given by the number 5 and 6. Or the outcomes in the event that the number is odd are E3, 1, 3, and 5. So event is as the basic concept in probability. Events are outcome and random experiment. Probability is defined in 2 main ways. The classical formulation is that the probability of a simple event happening is the number of times the event can happen divided by the number of possible events. So once again, if we roll a six-sided die, we can say, okay, the favorable event, so we aim to estimate probability of obtain 1, is given by 1 over all the possible events that are all the number from 1 to 6. So the probability is 1 over 6. But there is also another formulation based on experiment. So you physically perform some experiments and calculate the odds from your results. For example, what is the probability of a person making a basket? So we don't know at a priori, but we can say, okay, if you try to do 1,000 of shots, we can say at the end, okay, the probability is 3% or 20%, having the number of the person make a basket over all the trials. There are some special events in probability, and are basically two: the certain events and the null event. The certain event is an event that contains all possible outcomes in the sample space. So the probability of this certain event that we indicate with P and in parentheses E is equal to 1 or 100%. So the certain events. Or the null event is an event that contains no outcomes. And so the probability is equal to 0 or 0%. After this, we have three actions in the theory, in the probability, and these are at the basis of our calculation. The first one is that the probability of an event is a number within 0 and 1. Where 0 is the null event, 1 is the certain event. The probability of the certain event, so to sample something in the space of the events, is equal to 1. And the third axiom is that the probability of event 1 and event 2 is the sum of the two probability for mutually exclusive events. Mutually exclusive events are events that cannot occur at the same time. So, for example, are mutually events E1 and E2, because the occurrence of the number 2 or the occurrence of the number 5 or 6 cannot occur in the same time, of course. From these three axioms derive one of the most used equation, that is the complementary event, that is generally indicated as with a sign with a horizontal line upper the letter, that is given by 1 minus the probability of that event. So the complementary event of an event E1 contains all the outcomes in the sample space that are not in the E1. So for example, here it means all the number from 1 to 6 except the number 2. The other very important concept in PSHA is the conditional probability. The probability of an event E1 may depend, in fact, upon the occurrence of another event E2. So the conditional probability that we write in this way, so P E1 vertical bar E2, is defined as the probability that event E1 has occurred given that event E2 has occurred. So we use this formulation to solve this conditional probability. If the probability of the event 2 is greater than 0, means that there is some probability that the event 2 will occur, we can calculate the conditional probability with this ratio. If the probability of the event 2 is 0, of course, also the conditional probability will result in 0. So let's take another simple example to explain better these things. From a die, what's the probability that we obtain a value less than 5, but given that the value is an odd number? So here we have a conditional probability to obtain the set A, given that the value is an odd number indicated by the letter B. So the probability of A is 2 over 3 because it's given by a value less than 5, and we have four number 1, 2, 3, and 4. So in the figure is given by the circle blue. The probability B is 1/2, and the value is an odd number, so we have the number 1, 3, and 5. So if we calculate the conditional probability, we have to calculate the intercept that is indicated by this upside down U. So the probability of A intersect B is given by this 2 number at the end. So we have 2/6 of this probability. And having in mind the formulation we have shown before is 1/3 over 2/3. So the probability of A conditioned to the occurrence of B is 1/2. That is something different from the simple probability of A. So this is at the basic of our concept. And we can do another example, more adherent to our work, and also introducing another step forward, that is the total probability theorem. Because the total probability theorem is always used in PSJ, and this allows that we can compute the probability of A if we know the probability of the EIS and we know the probability of A given each of these EIS. Let's do a very simple example to understand this, total probability theory. For example, we have been asked to compute the probability that a building collapses during the next earthquake in the region. You don't know with certainty if the next earthquake will be strong, medium, or weak. And we can say that with strong, medium, or weak, we cover all the possible magnitude of the events. We can use this adjective, weak, strong, and medium. But some seismologists have estimated the following probabilities. Probabilities that the next earthquake will be strong is 0.01, medium 0.1, or weak 0.89. Additionally, for example, structural engineers have performed their analysis and estimated that the probability that the building collapses, given the earthquake is strong, so conditional to the the probability of collapse conditioned to the fact that the earthquake is strong is 0.9, and so on. Collapse given is medium is 0.2, or collapse given the next earthquake is weak is 0.81. So we can use the total probability theorem to put all together this information and calculate the total probability of collapse given by the probability that the building collapse during the next earthquake, given the earthquake is strong, multiplied by the probability that the next earthquake is strong, plus probability collapse given is medium, multiply probability medium, and so on. So at the end, we can easily use the numbers that seismologists, geologists, and engineers gave us to calculate the total probability of collapse. The total probability theorem allows us to break the problem into 2 parts. For example, in this case, size of the earthquake and capacity of the building, and compute probabilities for those parts. Then at the end, we can recombine them to answer the original question. I hope you can note that this not only facilitates solution of a problem because we split this problem in many pieces, but it allows different specialists, as, for example, in this case, seismologists and engineers, in the example I did, to work on different aspects of the problem. And for probabilistic seismic hazard analysis, is the direct application of the total probability theorem. The only exception we can see is that we use random variables that we will discuss later instead of random events. For example, the distribution of earthquake magnitude and distance can be studied independently of the conditional distribution of ground motion intensity. And we can see at the end of the talk how we can recombine this information to obtain our hazard assessment. So what's a random variable? The important concept, and we can see we introduce this concept that is very important, and also as the notation we use to indicate random variables. A random variable is a numerical variable whose specific values cannot be predicted with certainty before the occurrence of an event. And an event, for example, in our context, could be the magnitude of the future earthquakes. But for example, maybe also can be also not only the magnitude, but also the time to the next earthquakes, the distance, the ground shaking, and so on. The notation we use is the standard notation is to denote a random variable with an uppercase letter and denote the values it can take on the same letter but in lowercase. So for example, x1, x2, x3 denote possible outcomes of the random variable capital letter X. And we can talk about probability of the random variables taking those outcomes. And we indicate with this notation probability that the random variable X will take the value x1, for example. there are two main differences in the random variable if we treat discrete and continuous random variables. If the number of values a random variable can take are countable, for example, number one obtain the value 1, 2, 3, 5, 6, or in a die, or the number of earthquakes we can have in a region in a given period of time, this random variable is called discrete because it can take only countable number. And the probability distribution for a discrete random variable can be quantified by a probability mass function. So what we have seen before, the probability is that the variable x will take the value x in lowercase. The cumulative distribution function is defined as the probability of the event that the random variable take a value less or equal than the value of the argument. So it's indicated with probability that x will be less or equal than x in lower cases. Let's do the example. On the left, we have the probability mass function that can represent, for example, the number of earthquakes expected in a region in 100 years, for example. So we have a probability to have 0 event is 0.1, probability to have 1 event is 0.4, 2 events 0.3, 3 events 0.2. So we can calculate the cumulative distribution function. So, for example, the probability to have less than 1 event is given by 0.1. The probability to have less or equal than 1 event is probability of 0 plus the probability to have 1 event. So 0.1 plus 0.4, that means 0.5. And so on. We can compute the probability to have less or equal than 2, than 3, and so on. In many cases, however, we are interested in the probability that the variable x will take a value greater than, rather than less or equal. This is because we are interested in the probability of what is called a probability of exceedance. We can once again recall the complementary of what is the complementary of one event, and we can use simply to calculate the probability of exceedance of a given value, the formula 1 minus the probability that the variable x will take the values less or equal than what we are interested to see. If we treat with we are not treating with the, discrete random variables, but with continuous random variables. So we have to note that continuous random variable can take any value on the real axis. So because there are infinite number, the probability that a continuous random variable x will take on any single value is basically 0. So this forces us to use an alternative approach and introduce the concept of dx, that is the differential element of an infinitesimal length x. So actually we cannot calculate the probability in a continuous function, the probability of x, but we are calculating the probability of x plus dx, this infinitesimal length. And on the graph on the right, we have a plot of this distribution, and this with the shaded rectangle, I'm representing the infinitesimal length dx. This is a very important concept because we can compute the probability the outcome of x is between any two values a and b just by summing. The correct term is integrating the probability distribution function over the interval of interest. So the probability that will take a value, an outcome between A and B, is given by the integration of my probability density function by my function x over the interval. And a side note is that actually, we do not use continuous distribution, but continuous random variable, but sometimes we need to approximate continuous to discrete random variables for ease of numerical integration. One of the most important distribution is the normal distribution. This is a particular random variable that play an important role in all the calculation we will do. A random variable is said to have a normal, or sometimes say Gaussian distribution, if it follows the following probability distribution function. But what is important in this formulation, don't take care of the complexity of this formulation, is that this PDF is controlled by the mean value and by the standard deviation. And basically, if we plot the distribution, we can see that the mean value controls the position of the peak of the distribution along the x-axis. So, for example, the difference between the red and the green, you can see here the mean is 0, here the mean is -2. Whereas the standard deviation controls the shape. So if we look at the blue and the red, we have the same mean, but a different standard deviation. Again, if we look at the cumulative distribution function, we can see that the blue, the red, and the yellow, the brown curves share the same mean. And the peak is important because the peak divided this distribution into a symmetrical part. And in fact, if we go to integrate over all this number to build the cumulative density function, we can see that the three curves intersect at the same point where the mean is 0, and where we can see on the y-axis that we have 0.5. So it means that there is 0.5 of values below the mean. There is a 50% of values above the mean. The green curve, with the green curve, we have a different mean. The mean is -2, and in fact, -2 intercept return a values of 0.5. So this is a very important distribution. So we can, given the formulation, the simple formulation we have seen, the formula we have seen before, we can calculate probability. So, for example, the probability of an event occurring given a probability density function, and we will use a normal density function between two values A and B. In our works, it's particularly interesting to see what happens when these two these two limits correspond, for example, to plus or minus 1 standard deviation. So we can see, for example, what's the probability of an event occurring within 1 standard deviation of the mean of a normal distribution. So we built our normal distribution. When the mean is 0 and the standard deviation is 1, is also called the standard normal distribution. So this is the PDF we have built. We can calculate the cumulative distribution function, so it's summing all the values from left to right, and see what's the probability to that event occurring within one standard deviation. So we can calculate the probability that is minus than 1. Here is on the x-axis, there is the number 1, and we can see that this value corresponds to 0.84. The probability to the curves is equal to -1, this -1 standard deviation, is equal to 0.16. So this part of the curve is simply given by the differences. Probability that x is less than 1 minus the probability that x is less than -1. So it's 0.84 minus 0.16. That is equal to 68%. That is the magic number that we always listen when say, okay, there is 68% to have an event within 1 standard deviation. And this is the reason why we get that number. If we are interested to see the probability of an event occurring within 2 standard deviation, this probability is approximately 95%. 3 standard deviation is approximately the 90%, almost the 100%, the 99.7%. And this is these values are obtained just using this graphs and this calculation. The normal distribution is important in statistics, is often used in natural and social science, and it's also important because under some condition, we know that the average of many samples or many observations of a random variable with a finite mean and variances is itself a random variable whose distribution converges to a normal distribution as the number of samples increase. Moreover, Gaussian or normal distribution have some useful properties that are valuable in analytic studies. Main results and methods, for example, propagation of uncertainties, least square parameter fitting, can be derived analytically in explicit form when the relevant variables are normally distributed. But unfortunately for us, that the log normal is the normal. This because in geology and engineers, we treat with values that cannot take negative, with variables that cannot take negative values. If we think for example, to the ground shaking occurring during earthquakes, or to the length of a fault we are measuring, to the slip rate, we are always talking about positive number. We are not talking about negative number. So we cannot work with the normal distribution, but we can simply move from normal to log normal with a log transformation. So we have a new variable, for example, z, that is equal to the logarithm of x. So if the logarithm of x is normally distributed, then the distribution of x is called log normal. If we, for example, if we have recorded PGA for a magnitude 6 at a given distance, or we are measured the throw along a scarp, we have all positive numbers. So in the histogram on the right, we have all the values we have collected. If we build the cumulative distribution, the cumulative mass function, and we try to fit this with a normal and with a log normal distribution, a normal with the red and a log normal with the blue, we can say, okay, there are not so many differences here. But what is important is if we go to see what happened very close to zero. With the red curve, we will still have a probability that the x is less than zero. It's 1%, but there is this possibility. And this makes no sense to have, for example, a negative PGA or a negative throw measured along a scarp, or a negative length of the fault. So this is why we need to work. One of the reasons we need to work with the log normal. We have the same properties, so we can calculate the probability that an event is between plus or minus 1 standard deviation or 2 standard deviation. The only thing is that when we work with normal distribution, we can use addition and subtraction of the mean and standard deviation. When we work with log normal, we have to use times and division. But basically, we obtain we are working with the same object. But why we need to take care of this PDF? In our, for example, for a geologist, why we need to know what is normal, log normal, why we need to care about this PDF. I will prepare a simple example using an empirical regression between magnitude and area, and we will see another example using the ground motion. The first one, for example, using the well-known Wells-Coppersmith 1994 empirical regression, because I think all of us have used the regression in our scientific life. So usually what a geologist can do is to go in the field and measure the rupture area, measuring the length and the down deep length of a fault, and say, okay, I have a rupture area of 100 square kilometers, and I use the regression, the empirical regression, to obtain the magnitude expected. And in this case, for 100 square kilometer, I have a magnitude 6. So someone could say, if we assume that this rupture area is the maximum possible rupture area, then the maximum magnitude is 6. But actually, Wells-Coppersmith in their equation give us a standard deviation for this regression. In this case, it is about 0.24. Then we have to build a PDF of this regression. So, for example, for rupture area of 100 kilometers, the PDF is this one, where around magnitude 6 there is a peak in the distribution. But this probability density function also covers other values. I tried to plot and to rotate this PDF on the graph of Wells-Coppersmith, so probably you cannot read the number But trust me that here there is the 6 where there is the peak of the distribution. And so these blue curves should represent the uncertainties in this empirical regression. So what happened? Happened that is, if there is a rupture area of 100 kilometers, we have the 50% of probability that the magnitude is below or above 6. So the red line indicates that there is a 50% of probability that the magnitude will exceed 6, the value of 6. If we go to see what happened around the magnitude 6, we have obtained from our empirical regression, we can see that from within 5.9 and 6.1, there is 22% of probability. These uncertainties also mean that there is a very small probabilities, less than 1%, but there exists a probability that the earthquakes will have a magnitude less than 5.5. So take care about to say, okay, for a rupture area of 100 square kilometers, the magnitude is 6, because it doesn't mean actually it is not true. It's not representing what the Wells-Coppersmith empirical regression say. Another example, just a little bit more complicated, is given by the ground motion. Here in the graph on the left, we have the observed spectral acceleration for the Chichi earthquake in 1999. Given by the blue circle. And this distribution has been fitted by, for example, Campbell and Bozornia in 2008 with this model given by the mean is represented by the solid black curves and the uncertainties of plus or minus 1 standard deviation by the dashed line. The model to fit this ground motion generally follows this form. We work with the natural logarithm of the ground motion, for the reason I said before, is a function of the mean logarithm, that is function of magnitude, distance, and other parameters, many other parameters, for example, style of faulting, maybe VS30, the soil condition, and so on. And there is, of course, a standard deviation of these parameters multiplied by sigma, that is a standard deviation normal random variable. Positive values of epsilon produce larger than average values of the logarithm of the intensity measure I'm interested. Negative values will produce smaller than average values. So in this case, for example, is epsilon is equal to 1 for 1 standard deviation. Epsilon is equal to -1 in these other curves. One of the first model proposed or the first equation proposed to fit the ground motion, just to give credits to one of the first, is proposed by Cornell et al. In 1979, proposed the following form. Now there are 10,000 of models, very, very complicated. I used this one not only for credits, but also because it's very simple and easy to understand. I want just to focus on the meaning of these terms, not in the perfect fit. So the mean logarithm of the PGA is a function of some coefficient, but is a function of magnitude and distance. The standard deviation of this model is 0.57. So basically, we are interested into what is the probability of exceedance of a PGA level. We can indicate with this PGA level with X and say, for example, 1G using knowledge of the mean formula above this formula here, and standard deviation. For example, for a magnitude 6.5 occurred at the distance of 3, 10, or 30 kilometers. So we can use this formulation here and the complementary of probability, saying, okay, what's the probability that the PGA will be greater than a value X, given conditioned to the fact that the magnitude I observed as the earthquake I observed as a magnitude 6.5 at a distance and occurred at a distance of 3, 10, or 30 kilometers. This is the meaning of this notation. And it's given by 1 minus the standard normal cumulative distribution function. That all this value can be derived by using the magnitude and the distance in this formula. So, for example, magnitude 6.5 occurred at the distance of 3, 10, and 30 kilometers. We can calculate the mean value of the logarithm by substituting the values inside the formula and obtain different mean. So we are interested to see what's the probability of exceedance of a threshold. For example, 1G. So this is the same graph we have seen before. The solid is the mean. This is the probability density function, the uncertainties around the mean. And we are basically, this is the horizontal curves show the 1G, and we are basically interested to see what's the area indicated by the gray shadowed area. So it means that for the same magnitude, if I'm increasing the distance, this area will decrease. And effectively, if I use the formula before, I can calculate the probability PGI will exceed 1 at 3 kilometers is, for example, this area here is 0.16. But if the earthquakes will occur at 10 kilometers distance, I observe that the area is 0.043. If I'm at 30 kilometers, the probability is very, very close to zero. Not zero, but very, very close to zero. So this is what I mean with the probability of exceedance of a given threshold, given a model that fits the mean of the PGA. Just a side note is just to say that we always listen about the worst case scenario, worst case, the maximum magnitude, the maximum ground shaking. And as I think you have understood, worst case is done by choosing a nearby large magnitude event, but will be not the maximum possible event, as well as the same is for the ground motion. We are always talking about probability. So if we use the median, there is a 50% of exceed that value. If you use another percentile, we have a different probability of exceedance. But maximum magnitude and maximum ground motion are concepts that we should abandon. The Poisson distribution, we are in the block 3 because it's one of the most used distribution in our research. You always read papers and articles. You often see the probability of earthquakes happening in certain span of time. So the common statement is the probability of the magnitude 7 earthquakes hitting, I don't know, Tokyo in 100 years is, I don't know, 3%. How we can calculate this probability? Because we often use the Poisson distribution. The Poisson distribution is used to describe the events that occur very rarely, and is a discrete probability distribution, and models the number of events occurring in a certain interval of time. The most important parameters is the rate at which the events happen. The average number of events in an interval is often defined with the lambda. And Poisson distribution follows two main assumptions: independency and homogeneity. Independency, events must be independent of each other. So this is also why we said the Poisson distribution is a memoryless distribution. And homogeneity, the probability of occurrence, the rate or lambda, is constant through time, do not vary with time. So if the rate is 0.2, it will earthquake per year, it will be always 0.2 earthquakes per year. For example, if I have a record of 4 earthquakes with magnitude 7 in 200 years, I can say that lambda is 4 divided 200, so it's 0.02. This is the annual rate. The probability mass function of the Poisson distribution is given by the formula. If I am interested to see what is the probability of one event, given this lambda, of exactly one event, I can put 1 instead of the x, and this is the annual rate, and I get the probability that is 0.0196. If I'm interested to the probability of exactly 2 events, I will put 2 instead of x, and I get another value. But actually, we are interested to see what's the probability of at least 1 event. There is something different. And the probability of at least 1 event, it means, as we calculated before, 1 minus the probability of 0 event. So the probability of at least 1 event, that means x will be greater or equal than 1, is 1 minus the exponential of lambda. If we put 0 at the x, we get this formula here, and so we can calculate the probability of at least 1 event given the annual rate is approximately the same annual rate. But what about, for example, in 10 years? If we are interested to see what happened in 10 years, given the same annual rate, we just simply multiply the lambda here in the formula in the center, the lambda multiplied by the time of interest, in this case 10 years. So 1 minus the exponential minus lambda times 10 years is 0.18, and so on. An important note is that the sum of 2 Poisson random variables with parameters, for example, lambda 1 and lambda 2, is again a Poisson random variables with parameters lambda given by the sum. So the example in our case, it could be if lambda 2 is the annual rate of magnitude 6, for example, we have 15 earthquakes in 200 years, we observed. The probability, what's the probability of at least 1 event of magnitude 6 or 7 is we can calculate a new lambda by the sum of the 2 lambda for magnitude 6 and 7. We get the lambda, and we can calculate the probability of at least one event in 10 years, that you can see is about 60% or 0.61. The Poisson process is very important because it satisfies the independency assumption and has been extensively used in seismic hazard. An important note is that if the occurrence follows a Poisson distribution, the inter-events follows an exponential distribution. So the Poisson distribution deals with the number of occurrences, and the exponential deal with the time between occurrences. So if we have a set of occurrences of an event, and we calculated all the inter-events time, we can try to fit this inter-event time with an exponential distribution. Just for graphical purposes, I put the normal distribution to show you that the distribution of inter-event time is more coherent with the exponential distribution. So this is an important concept. The block number 4 is the Gutenberg Richter. I don't want to spend much time on the Gutenberg Richter because, not because it's not important, but because it's so important that I hope we will have another lecture or a jamming series in the future focused on this. So we know what is the Gutenberg Richter, and we know why it's very important to estimate the p-value. For example, this is just an example. If we have 10,000 magnitude greater than 4 earthquakes with an error of b-value of 0.1, I mean, if the b-value estimated is 1, I expect 10 earthquakes with magnitude greater or equal than 7. But if I estimated a b-value of 0.9, I expect 20 magnitude earthquakes with magnitude greater or equal than 7. The classical method used to estimate the b-value is described by Aki in 1965, and it's based on the maximum likelihood estimator approach. What is very important is that we have to estimate the mean of the magnitudes and the minimum magnitude of completeness. These are the 2 most important parameters. And what are the most common errors we usually do? I will show I individuated 4 most common errors. I will show you just the number 1 and the number 3. The first is fitting the data with a less square instead of maximum likelihood. The data set is too small, or we are using earthquake smaller than the catalog completeness. And then there is a 4th error using data with magnitude errors. The first common error I read in probably in very old paper, not recently, is to fit with a least square. Least square assume that the error at each point follow a Gaussian distribution rather than Poisson distribution, and assume the error on each point is equal. So at the end, maybe you can get from a visual point of view just a very line that fits very well your point. But note that the least square is disproportionately influenced by the largest earthquakes. Instead, the maximum likelihood estimator weights each earthquake equally. So this is one of the first common error I see. The other error is using earthquakes smaller than the catalog completeness. So if we see the Gutenberg Richter of the earthquakes in the cumulative form, and to be more precise, is in the survivor form, if we start to fit, for example, this distribution starting from magnitude 2.5, we get a value of B equal to 1. But if, for example, we start here at magnitude 1.5 or magnitude 1, we will get an earthquake B value that is different, 0.9 or 0.8, and this will produce the differences in the number of events expected at the higher magnitude. The other error is the completeness, using if the completeness of our catalog vary with the magnitude. This is because I usually use historical and instrumental earthquake catalogs, so I have to define what is the period of completeness, and there are two main models, I say, two members of model. This is an example for the central Italy with the solid curves are the results of the historical completeness approach and with the dashed line with the statistical approach. And you can see there are different thresholds. The historical method is basically based on something that is external to the catalog. So, for example, we have some people that wrote about the earthquake's effect in some towns, and so we can say, okay, we have historical records that have been preserved, and we can say, okay, for magnitude 6 and above, probably I'm here. I have all the records starting from the 12th century and so on. With statistical methods, instead, are based on the earthquakes contained in the catalog. For example, there are many statistical methods. For example, here the authors use the Albarello et al. 2001 approach, the time to define the time interval characterized by a seismicity dataset representative of the actual seismicity. So they derive the completeness using data that are inside the catalog. Historical methods, for example, use data that are outside the catalog. Just to conclude about the Gutenberg Richter, how many Gutenberg Richter exist? Because we always talk about Gutenberg Richter, but actually exist different forms of the Gutenberg Richter. There is a nice paper by Kagan, 2002, that shows us that at least 4 different Gutenberg Richter exist. And here is a focus on the highest magnitude, where we can see the difference about these 4 distribution. We generally talk about the Gutenberg, the number 1, that is the characteristic distribution. I mean, the Gutenberg Richter is hardly truncated at a given magnitude, so there is a straight line, or you can have a sort of tapering at the highest magnitude. We have the truncated Gutenberg Richter that is always has an hard cutoff, but tends to this hard cutoff with the tapering. Or we can have a tapered Gutenberg Richter or a gamma distribution that basically has no upper bound. So they go to, or they can take all the magnitudes values. And I think this is an interesting topic to treat in a separate session. So just to go to the conclusion, because we have now all the bricks to build our hazard curves, and as I think Graham Wetherill in one of the last talking series show us how to calculate what is the hazard integral. So basically, I want just to recall that the hazard integrals can be divided in two parts. One is we can say attributed to the seismogenic source, in particular the rate at which the earthquakes occur, and one is basically given by the ground motion, the probability of exceedance certain level of ground motion given the occurrence of magnitude at the earthquake with a given magnitude at a given distance, what we have seen before. The first example, so if we have a fault A that can give us just only magnitude 6.5 for simplicity with a rate of 0.01 times per year, and this fault is located at a distance of 10 kilometers from our site. We can calculate the median ground motion using always the same equation, the logarithm of the PGA given 6.5 at a distance 10 kilometers, and we obtain the logarithm that is minus 0.9788. Then we defined a vector of intensity measure we have calculated before, just the probability to exceed 1G, but we can calculate the probability of exceedance, for example, 0.01 or 0.1 or 0.3G. For the earthquakes with that magnitude at the distance, and multiply this probability of exceedance by the rate of occurrence of that earthquakes, that is 0.01, this lambda value. So for 0.01G, the annual frequency of exceedance is given by this multiplication. For 0.1G, is another value, and for 0.3G is again another value, and so on. So actually what we did is to calculate for any values of PGA intensity threshold the probability of exceedance. So what we represent with a curve is actually a vector of point. Here, for example, we can see again the probability of exceedance 0.3G is here, the probability of exceedance of 1G is here, and so on. If we build for many values of PGA, we can build our curves. I prepared a simple Excel spreadsheet where you can change the magnitude, the distance, the sigma, or the rate to obtain the X and Y axis shown here. So if you are interested, I can send you by mail. The second example, if I have two faults, one that gives us magnitude 6.5 with this rate, and the second one that is located at a distance of 20 kilometers and can return magnitude 7.5 with this rate. So we just did the calculation for the fault A. We have to do the same calculation with the fault B, just varying the magnitude and the distance in our equation to calculate the median logarithm of the PGA, and using, of course, the appropriate lambda, that is, in this case, is 0.00002. So for the same PGA threshold, we calculate the annual rate of exceedance, and we build another curve. So for the fault A, for example, we have the red dashed line. For the fault B, we have the point dashed line with color blue, and for each PGA level, the total hazard is given by the sum of the contribution of the fault A and the fault B. So we are using the total theorem probability to calculate our total hazard. It's also interesting to note, for example, here is that which fault mostly contribute to the hazard depends from the PGA we are interested to observe. For example, for low value of PGA, 0.3, 0.4, the fault A contributes more to the total hazard than the fault B. But is the opposite if we are interested to probability of exceedance of 2G, for example. If we have the last example, if we have one fault, but with that can release earthquakes not only of magnitude 6 or 6.5, but from, for example, from 5.5 to 6 with rate of occurrence of each magnitude, how we can calculate the total hazard? We just simply treat all the magnitude as an individual source. So, for example, we again, using magnitude 5.5 and the distance of 10, we calculate the median ground motion. Then we use magnitude 5.6 and always the distance 10, and so on. And we have to multiply, to pay attention, to multiply each median logarithm by the appropriate lambda. So we have to build we have to calculate a lot of annual rate of exceedance. For example, for 0.1g, the lambda of the magnitude 1, for 0.3g, the lambda of the magnitude 1 of exceedance multiplied by the probability of exceedance 0.3, given the same magnitude, and so on. So we did to do a lot of calculation for the same for all the magnitude using the appropriate lambda. Again, I have prepared the Excel where you can see all the calculation. But at the end, what is important is that we obtain an hazard curve for each of these magnitude. And the total hazard is once again given by the sum of the annual rate of exceedance of the 1, 2, 3, 4, 5, 6 magnitudes. We sum the annual rate of exceedance of the 6 magnitudes to obtain the total hazard. Speaking, I always usually speak about annual rate of exceedance, but sometimes you read about mean recurrence time. So this is just one is the inverse of the other. So if a given ground motion intensity has a 0.01 annual rate of exceedance, the return period is 1 divided 0.01. Unfortunately, this mean return period is sometimes confused with the mean return period of the earthquakes, but these are completely different things. Another way to see this rate of exceedance is to speak about probability of exceedance. And to move from rate to probability, we use once again a Poisson model. And so if we use a Poisson model, we can calculate the probability of at least one event, in this case of at least one exceedance of a given value of PGA in a certain time t, using the same formulation we used before. So, for example, if we are using a period of 50 years, as commonly used, and the annual rate is 0.0021, it means that we have a probability of exceedance of this value of PGA that is 10%. If the annual rate is this number here, the red number here, we have a probability that is 2%. If the annual rate is 0.033, it means that we have a probability in 50 years of 80%. So it's basically the same things. Speaking about annual rate of exceedance, mean recurrence, mean return period is one of the inverse of the other. Given fixing these two values and given a time of interest, we can calculate the probability of exceedance in the time of interest. Focusing on for example, on the point B on my hazard curves. With this annual rate of exceedance, 500 more or less here of return period. If the time of interest is 50%, in 50 years, I calculated the probability of exceedance of 10%. But if the time of interest is not 50, but is 30 here, then the probability of exceedance is 60%. So pay attention when you read the paper, what is the probability is a function of the time of interest. So it's basically always equivalent to say, for example, for the point B, PGA of 0.6G has a probability of exceedance of 10% in 50 years or 6% in 30 years to be exceeded. Or we can talk about the mean return period that is 470 years, or an annual rate of exceedance that is 0.0021. These are always the same. We are talking about the same object. the last slide is to say that I used just one source and one site. But if we repeat this calculation for all the sources I have, I will sum all the other curves for multiple sites and for other spectral acceleration, not only PGA. I will build so many other curves. And if I'm interested to probability of exceedance, for example, PGA with 2% in 50 years, I will take the value from these curves and I will plot this value in a map. This graph here should represent a map where each square is a site, and the colors are proportional to the PGA. So I'm just cutting my other curve with an horizontal line for all the sites to build my map. If I calculate not only the PGA but also other spectral acceleration, for example, 0.3 seconds or at 1 second, I can build map not only at PGA but also at spectral acceleration of 1 second and so on. And if I take these values from the PGA, from the other spectral acceleration, with the same annual rate of exceedance or the same probability of exceedance in 50 years, or the same mean recurrence time, I can plot this value in this graph that is called uniform hazard spectrum, UHS. So that gives us the values plot just in a line, all the values that have the same probability to be exceeded. So to conclude, I hope you have basically have an idea of how we can calculate another curves, what are the problems, why we need to take care about probability density function, and basically that when we calculate hazard, we calculate hazard curves. Then engineers or building codes ask for particular mean return period or probability of exceedance, and that the other model is not a map. These have a lot of consequences also when we are going to compare what is for example, the classical PGA map with 10% of exceedance in 50 years with the occurrences of a single earthquake. So what we observed, this is basically a big mistakes that we sometimes see in many papers. So another model is not only a map. This is the conclusion. I hope you are still alive.
Francesco, thank you so much. If anyone has any questions, please raise your hands and we can go to you. Probably have time for just one or two very quick questions. While people are thinking about that, I just wanted to remind everyone about our next Fault2SHA Learning Series, which will be given by Rachel Abercrombie. She'll be talking about estimating earthquake stress drop, resolution, and uncertainties, which is on Monday, the 11th of July. Please notice it's 1 hour later. So at 3 o'clock for those of you in mainland Europe, and 2 o'clock for those of you in the UK. This is to allow her a little bit more sleep as she's speaking from Boston University. If there's anyone who would like to ask a very quick question to Francesco, please do so now. Raise your hand. If not, I think it was all fantastically explained. Francesco, thank you so much. You went through everything in such a good systematic way. Really, really appreciated, as always. And I'll say to everyone, thank you so much then, and see you all next time.
Thank you very much.
Lots of messages in the chat saying thank you. Great. Thank you, everyone, and see you next time on the 11th of July.